chemical kinetics. Now here in this module, we will understand the effect of positive catalyst on rate constant. In the previous module, we saw how temperature affects the rate constant, and now we will see how a catalyst affects rate constant. I'm sure you remember this particular slide from one of the previous modules. Here we had studied that catalyst is among those factors which affect the rate of a chemical reaction. And what exactly is a catalyst? Well, if you remember, a catalyst is a substance that alters the rate of a reaction, but it is found to be chemically unchanged at the end of a reaction. So it alters the rate of a reaction and it remains chemically unchanged at the end of the reaction. We had understood how a catalyst works with the help of this graph. We had energy on the y-axis and reaction coordinate on the x-axis. Some reactants get converted into products, and this is the energy profile diagram. So the reactants have some energy which is represented by this dotted line here. Now these reactants, they absorb some energy, and when they absorb some energy, they reach a level here. Now this differential is called as activation energy, but this is without a catalyst. Now beyond this point, the reaction becomes self-sufficient, it becomes spontaneous. Now what a catalyst does is that when you add it, it drops this activation energy. So now you can see this is the new energy profile diagram, the green one, and this new differential, the smaller difference. This is nothing but the activation energy with a catalyst. A catalyst has dropped this activation energy for the reaction. Because of this, the reaction becomes faster. Well, let's understand that with an example. You've got hydrogen peroxide, which is decomposing. This reaction, decomposition of hydrogen peroxide to give water and oxygen, it requires 76 kilojoules of energy. But when this reaction takes place in the presence of a catalyst, that is iodide, this reaction now takes place in only 57 kilojoules. So yes, the presence of a catalyst has dropped the energy of activation. Because of that, the reaction becomes faster. If you remember, we had also seen this particular diagram to understand that. This guy over here going through the tunnel, the activation energy is low, so the reaction is fast. And it's the opposite for the other guy. So yeah, by now I'm sure we all have understood that a catalyst provides an alternate pathway of lower activation energy, which increases the rate of reaction. Now this can also be understood with the help of the distribution given by Maxwell and Boltzmann. You can see their photos here. Now this Maxwell-Boltzmann distribution of molecular energies, it's nothing but fraction of molecules on the y-axis versus energy on the x-axis, and this is the distribution. Again, if you remember where this black dotted line meets the x-axis, this point, it's nothing but most probable kinetic energy. Now, this point right here on the x-axis is the activation energy, and the entire fraction of molecules ahead of it, it is nothing but the fraction of molecules capable of effective collisions. These molecules, this particular fraction, the gray part, when they collide, you get products. Now when we add a catalyst, what happens is, when we add a catalyst, this activation energy, it decreases. And due to the decrease in the activation energy, now the fraction of molecules which are capable of effective collisions will naturally increase. So since the activation energy decreases, the fraction of molecules capable of effective collisions increases, and this increases the rate of reaction. Well, we can also understand this with the help of Arrhenius equation. Again, Svante Arrhenius. We know the equation K is equal to A into e raised to minus Ea upon RT. Now, when we add a catalyst, we know the activation energy decreases. When activation energy decreases, naturally, Ea upon RT will also decrease, because Ea is the numerator. So if it decreases, the fraction value will also decrease. If Ea upon RT decreases, what will happen to minus Ea upon RT? Of course, it will increase. Now, when minus Ea upon RT increases, my dear students, E into that whole term, minus Ea upon RT, it will increase, because now the power is more. So you can say that A into e raised to minus Ea upon RT will increase, and because of this, the value of K will now increase. So we have seen how addition of a catalyst drops the activation energy, and because of that, the rate constant increases. So always remember, when you add a catalyst, activation energy decreases, rate increases, and rate constant will also increase. That's all for this module. Thank you.